データスタックスのアルトビと申します。私は Apache Cassandra のオープンソースエヴァンジェリストをしています。ここからは英語でお話しします。So I'm, as I said, my business card says open source mechanic. And it says that because I come from an operations background. And prior to coming to DataStax, I operated Cassandra clusters for a company named Utala. I came to DataStax because I was impressed with the technology and wanted to do more to get it out there in the community. So that's my job now, is to come to talk to people like I am now and explain what Cassandra does, why it's useful to your business. And today I'll be talking about consistency with Cassandra and a different way of thinking about it. So I work for a reason. These are my boys. Just wanted to show a picture. I have one of my dog later, so I thought I'd put one of my son doing the same thing. I did not have permission from my wife to use her photo. So a little bit, just leading into the consistency part, I want to talk about why it's important to consider consistency when you're designing your application and your data model. For example, in Japan today, according to Wikipedia, there are 140 million active cell phones. Cell phones are used daily by everybody here. When you have an application relying on a database, such as an SMS system, we have customers that use Cassandra in SMS delivery systems. And if the database goes down and SMS messages don't get delivered, customers get very frustrated, get very upset. It's bad for business. Many customers, very popular application of Cassandra is for mobile applications, for game scores in the games you play when you're riding the train, for items that your character owns in a massively multiplayer online game. So there are 100 million internet connections active in Japan, again from Wikipedia. Across the world, we use the internet for everything today. Everybody knows this. For B2B, video conferencing. I talked to my son this morning over Skype, who is still in America. We use it for shopping, entertainment, and we use it for sometimes human critical situations where safety may be at risk. And the internet never sleeps. It's 24/7, and it's unpredictable. Things fail. You get load spikes. So that's just to lead into a little bit on architecture. I'm going to talk about a few traditional architectures to lead into what we do with how to do it with Cassandra. And this one, this goes all the way back to the birth of databases. Client server, very simple. Today considered quite obsolete. The red circles are clients, and then the cylinder is the database. And many, many years ago, you might have a client on a user's workstation directly accessing the database without a middle tier. Please don't do that. But it's the original funnel-shaped architecture. And the funnel shape is kind of the main thing that I look for when helping customers. When I see their architectural diagrams and I see many clients coming down into a single database, then you start to see that that's where the bottleneck usually is. Once we get to Cassandra, the funnel ends up elsewhere, but it's something to look for as a pattern to avoid. So most architectures based on traditional databases today look more like this. the standard 3-tier architecture. The blue circles represent the application tier. So this is your traditional LAMP, Linux, Apache, MySQL, Perl, PHP, which through 2000s, the early aughts, that's what was common, or even most Ruby on Rails architectures. And then later on, we add caching. It's more complex. And now you have a new problem to deal with, cache coherency and validation. So I'm talking about this for a reason, which is, as we scale out, a lot of the methods that we've used in the past to make applications scale trade off performance for complexity, or complexity for performance. Cascading failures are a problem in these architectures. And it's difficult to manage just because there are so many moving parts. This is how I kind of think of most Cassandra architectures, or things built around Cassandra. I left some lines out to keep it easy to look at. But the idea is that you have many, many clients, many more than what we've been able to support in the past. And they talk to many application servers. And then in the center, there's a database that now, instead of being constrained by the capability of a single computer, can now be spread across many computers. And many of you have been here, seen other talks, you know this part already. And we're making trade-offs. This is what I'm coming to, is it's all about these trade-offs. Now you need to scale out even further. Load is doubled, it's tripled, it's quadrupled. When I worked at Uyala, during the time that I supported Cassandra there, the traffic that was supported by the Cassandra database, the data that went into it, went 10x twice. From an 18 node cluster to 36. But 10x, 100x the load. And the reason why that worked is partially because the data model was correct, and partially because the database was correct. One of the things that they did wrong was the data model. So this is an example, very simple database model, the classical employee person. So in this case, what I want to talk about is read, modify, write is the anti-pattern. Almost everywhere where you're dealing with performance tuning, and as I mentioned, from an operations background, that's what I spend most of my time doing, was performance tuning. What I'm always looking for is where is the read, modify, write cycle occurring. So this is actually, I'm pretty sure this is actually valid SQL and CQL. So what we're doing is, in this case, is taking a record that's already in the database and changing 2 fields in the same object on storage. What that means is now the database, instead of being able to just record the change, record the delta, and some of them might do this, depending on the design. But now they have to take the record in memory, sometimes pull it from disk, mutate it in memory, and then write that mutated record back to storage. And make sure that that all happens in the correct order so that you have consistent data when it's all done. And when Cassandra was started, and as it developed, this is the problem that Jonathan and others were trying to get around, is how do we get around this limiting factor? And for my English friends, this is the Japanese translation some friends helped me with for there's no such thing as a free lunch. I hope it translates well. And what it means is everything we do in technology, or really anything, there's always a trade-off. There's always something has to give for something else to get faster. So in the case of read, modify, write, when you go into distributed systems, now you have many nodes in play, and they all have their own idea of what the data looks like and how to make it converge. It's more complicated. So we've already traded off complexity. Ideally, and most of the time, Cassandra takes care of hides a lot of the complexity for you as an application developer. And for operations, it's getting a lot better. So it gets extra complicated when you talk about failures. So when a node goes down, this red circle, let's say that node fails in the middle of a transaction. It had one idea of what your mutation was. It said that I got promoted. And if the other nodes that it replicates to did not receive that information before it went unavailable, I might not get my raise. So I don't want that. We have backup systems built into Cassandra. I'm not going to talk about those today. What I'm trying to point out is there's a lot of complexity in making consistency available to you from the database side, especially when a lot of huge multi-core machines connected to an asynchronous network are all trying to agree on something. And we can see this in almost any distributed system we build. And pretty much anything that with more than one computer, or really more than one microchip, is a distributed system. So, getting away from read, modify, write. It still happens at some level of the system, but there are patterns that we can use in our data models, in our systems design and architectures that help move past the limitations, at least from the sense of the database. So one of them is, and I'm going to go through each of these. Overwrites, which means overwriting the same cells over and over in the same place, which is, it sounds like it might be the same problem all over again, but we're leaving a read out of the loop. We're just, when there are many application patterns such as device logging. You have an application that you just want to report each time somebody clicks on a certain button. That message can be written in multiple times to the database, and it doesn't matter. You just overwrite it and let the database sort it out. There are limitations. There's key value, the old familiar memcached style, where you do pretty much the same thing. There's the journaling or logging or time series data models, which is probably one of Cassandra's more popular use cases. Content addressable storage. If you've used Git, you've used the content addressable storage. And Cassandra, finally, when you need to use read, modify, write, Cassandra has facilities for supporting that and making them consistent. You heard Jonathan talk about them earlier, which are Cassandra's collection types and Cassandra's lightweight transactions. So for the overwrites, here's the CQL basically to set up an overwrite situation. I worked on an application a couple years ago that used Cassandra for time series data, but one of the problems we had to solve was the metadata from all these systems, their host names, their EC2 instance IDs, various different host names. Some of these servers had multiple names on the network, multiple addresses, and users wanted to be able to look them up by any one of those names or addresses. And so, in traditional way, you have a lookup table. One of the nice things about the architecture, the way it ended up, was rather than trying to make sure that the data was sent by all of the systems and having lots of synchronization and applications checking the database to see if its write went through, all we did is we set it up to send the information once an hour. Sent the same information all day long. Every hour, every system sent all the information. And we just wrote it into the lookup table straight through. There was no check, there was no lock, there was nothing. Basically the message popped out of the client on the servers, about 22,500 servers. They would pop a message, it would get written into the database. And just overwrite. So this insert into, for the same machine, would overwrite the same record every time it fired. And this means I don't have to worry about the read, modify, write scaling problem. It's not something, just like all of these cases that I'm presenting to you, they don't all work they have very narrowly defined scopes where they work well. But for some use cases, this one works really well, especially on a distributed system like Cassandra. Some other places where this really makes sense is when you're managing your own indexes. You can have batch systems that process all of your data, say Hadoop, or even a custom designed system that reads through your records in a column family and generates a specialized index and writes that into a new column family. Rather than reading the old index to make sure that everything is the same, you can just overwrite it, sometimes. This is a traditional key value setup. It's very simple to set up in Cassandra. This isn't something that should be used very often at all. But in cases where you want something that feels a little bit like memcached, you want to keep the architecture simple, and it's not going to be an extremely loaded use case. And this is an oversimplified schema. Spend some time. All of these examples are going to be highly simplified to fit on slides, and so we can go over it all in an hour. So with that disclaimer, this works. We had use cases at UYALA where we did this, where we had applications that were already connecting to Cassandra and they wanted to cache some values. And users came and said, we want to use Redis for this. We want to use memcached, Tokyo Cabinet. And my team said, what is how many messages are you going to be writing every second? Do you care if that data goes away? Does it matter if memcached crashes? How badly does a cold cache hurt you? And it turned out a few times that it made more sense to have them just reuse the Cassandra connections they already had to get the same data. And it has a couple of advantages over the specialized solutions like memcached. Number one, you don't have to worry about cache coherency across multiple cache implementations. You have the uptime of Cassandra. On the downside, you have the cost of Cassandra, where you have to have 3, 4, or 5 nodes to start. But it's a useful pattern at times, and it's a great way to get started. Playing around with Cassandra, writing a small sample application. It's one of the simplest you can write. And time series data is probably the most important, in my opinion, not everybody's, most important data modeling tool to understand in the modern age. So much of the data that we're collecting as part of what we call big data is really time series data. As I mentioned, a cell phone game reporting items that users won can be modeled as time series. If website usage can be modeled as time series. There are a lot of things can be modeled as time series that on the surface and at first glance you might draw up a traditional entity relationship diagram for a relational database and start storing those records. But if you dig a little deeper and look at time as a dimension for all of your data, especially big data, and you use that in your data model, you can get much higher performance very often. Simpler systems, because now your applications don't have to be concerned with versioning data, or making sure that cells get updated. Especially when we talk about lightweight transactions. A lot of these problems can be solved by applying lightweight transactions, but the Paxos overhead is really high. So if you can model as time series or one of these other models instead, it saves a lot of CPU time. So a little bit about this model. So the important parts for any time series data model is what we call a bucket or time bucket or a partition if you prefer. And it basically, you have to decide at what time interval do you want to partition your data. So you might decide to change containers or keys every 5 minutes, 10 minutes sometimes. Usually you go 5 minutes one day are really common. I haven't seen many over a day. Sometimes I've seen a minute. If it's really, really high data rate, you could go smaller than a minute, but it's fairly uncommon. So that's what I'm referring to time bucket here. What that's going to look like is an RFC 8601 date that only has the date for a daily bucket. Or if we were doing minutes, you would just stop at the minute marker. And this becomes your partition key. And as a note up there, UTC, a recommendation. I've seen this out in the field. Whenever you're writing dates into a database, whenever possible, the business doesn't have a good reason not to, I recommend converting all times to universal time before writing to the database. And it sometimes seems like it's not worth mentioning, but I've seen time zones inside databases, and it's usually ugly after a couple of years. So as the column key or the cell key, we put the full resolution time. Again, using RFC 8601 format. This could be higher resolution time, including seconds, microseconds, nanoseconds. Nanoseconds are a funny one. If you've done any research on Intel 386 clocks, they're a complete disaster. They change times. I've seen servers that will pick up 15 minutes in an hour, or they'll sometimes jump time around, which leads to just a side note, which is always make sure that the servers that your code is executing on are running NTP or some other time synchronization system. Anytime you're dealing with Cassandra, or really any distributed system, this is extremely important, more important than it was in the past. Because time is a really critical component of everything you do in these large-scale systems. And then finally, as the value, I have a blob, which is just binary large object. But we can put whatever we want in there. It can be a little bit of JSON. It could be protocol buffers or message pack. We don't generally recommend that you store these serialized objects this way if it can be avoided. But for the sake of keeping the example simple, I showed that there. It works. It doesn't scale as far, and there are downsides in terms of schema management. So if you can, use Cassandra's types to fully flesh out this table structure. And if you went to Aaron's class, I'm pretty sure he took you through that. But this is the basic, simplest time series data model. So moving on. This is kind of what it looks like I have a couple different ways that I visualize this, especially when I'm explaining it or explaining it to product managers or non-technical people. It's a little bit easier to show it this way. The bottom one is what I show technical people when they're trying to figure out Cassandra's data model. So this is the same stuff we saw in the inserts, right? Here's our time bucket. So everything generated on January 24th. We have 2 records in here. One that happened at 12:12 and 12 seconds, and one that happened at 21 hours and 21 minutes and 21 seconds. Pretty simple. A lot of different data can be fit into that model. And then finally, for this one is just, it's a different way to look at how Cassandra data can be modeled mentally. I run into a lot of people that, especially before we brought CQL in, had a hard time understanding how to model data for Cassandra. And the nested map tends to be useful enough to keep it around way to think about it. Jonathan disagrees, I think, but I still find it useful, especially for younger programmers. So you could say your time buckets are your first level key, and you might have the second one here, down here. Your second level is your full timestamp, and then your values are whatever data you're storing. It can be useful to think of it in terms of two-level nested maps. Content addressable storage, it's a little bit harder to come up with ways to explain how this works. The most common system using this today is Git, the source control system, as I mentioned earlier. And what this means is, in order to address your objects, you use the value of those objects to generate an ID that's unique to that particular set of values. It can be almost any strong checksum algorithm, SHA-1, MD5, those are both perfectly valid. So here's a little bit of Ruby, just kind of showing the concept. The data.2s in red, it's in red because this is a terrible, terrible thing to do, but it's just to demonstrate the idea. So if I have a piece of data, has a timestamp and a value as its members, and this is a map. I take the data, I serialize it, and there are better ways to do this, to optimize this. But the general idea is I can take that, serialize it, take a SHA-1 checksum of it, and then this unpack just puts it in hex. And then that's how I address the object in the database. It's tricky to use these systems. Very often they're useful for archival, to replace things like object storage systems. I think ZOPS, ZODB, used to be a content addressable system. It's just one more model worth thinking about. Occasionally, not very often, as often as time series, it's useful for storing data. And again, there's no reason to ever have a lock. You can have an entire distributed system at reading and writing objects, for the most part, without a lock, depending on how you manage the indexes into that data, right? So if you have a list of 1,000 objects, and it's content addressable, managing that list is the hard part, but it's a much smaller volume of data than the bulk of the objects that you're storing. So in the case of Git, you might have 1 million diffs stored in objects in the Git storage system. And these are commits that you've made to your code over time. The index into that is the tricky part, where you have to synchronize and be careful. So it's just a set, and you could actually use a Cassandra set for it, incidentally. But what makes Git fast is that the backend doesn't require any synchronization to store objects and to retrieve objects. If the object exists, then it's there and it's consistent. If it doesn't exist, then you just write to it. And with algorithms like SHA-1, which is 160 bits, or SHA-256, 512, which are both quite fast and useful algorithms for this, you're pretty much guaranteed to never have a collision. So in practice, we can't always avoid read, modify, write. Sometimes, like those sets I mentioned earlier for content addressable, you need to actually have a way to say, I need to do an atomic write that is guaranteed to be stored consistently so that when the next reader comes along, they get exactly the data that I just wrote. And we provide the tools for that. From Cassandra 2.0 up and forward, we have lightweight transactions, and we have the collection types, which are actually a form of CRDT, which is the I'm drawing a blank on the definition right now. It's not terribly important, but what is important is the database ensures consistency on updates when you write to those sets and maps. Generally, lists are a little bit, use them for advanced use cases, but maps and sets in Cassandra are consistent. So on Cassandra collections, maybe you have I have a story for this one first. So I was putting this together, and this slide deck together, and when I came to this one, I wanted to put, I've been learning Japanese for about 8 or 9 weeks, just to hopefully be able to get around without really stepping on toes and getting totally lost. And so as practice, I've been using it whenever I get a chance, and what I wanted to put in here was just a little bit of content. And so this is supposed to be posts maybe on a blog or something, or a little Twitter clone. And so here, I thought, well, there's this phrase I've been using with my dog and my son, which I watch anime, and one of the phrases you hear a lot that most Americans know is baka. And so when my dog does something incredibly annoying or silly, I'll get my son to say, he'll go, "Ino baka ne," or "Ino baka yo," and it amuses me. And so I tried to explain this to my Japanese instructor, and it took about 15 minutes before, and then it finally ended with her just shaking her head at me and wishing me a nice day when I left. But this is my dog Rufus, and he just played in the mud and wanted to come inside the house, and I took a couple of pictures first before hosing him down. And so that's why it says my dog is Bucko. And I understand that doesn't, in America we call dogs stupid or silly all the time, and it's kind of a cultural thing. Anyway, so I have a table of posts, and these can be a standard data model. Maybe they're addressed by a UUID. I track which posts go where on my website somewhere else. It's not important right now. I have a body which has some text that says what I'm thinking today. I say when I created it, because if people are looking at it down the road, they want to know when. It's all very clear. And then I might have, for author, if I was designing this when I was younger and less experienced, I might have just had a varchar there and assume that there's only ever going to be one author. But in reality, things tend to grow out of your original intents. And so when I created this, I thought, well, I want to have multiple authors. But instead of what I would do in a relational system is I would create a post authors table and have a relation to posts and then do a join. But that doesn't really scale. And so we have these nice sets in Cassandra that'll let you have multiple authors, as many as you want, and it's all maintained in the database for you. And so we have 2 authors on this post, which is me and my son, Leo, which is why I put his picture at the front. It's coming up later. So these are guaranteed to be safe to update in place with an update post set. I didn't. That was silly. I'm Baka now. So these are really handy. You can use sets, and you can have the maps, which are basically key value embedded inside your tables. As Jonathan mentioned, with the extended types coming in 2.1, you'll be able to put other types in there and have nested sets, nested maps. And now you don't need to have separate relational tables, which saves you round trips to the database. And now you have a much higher performance architecture. This is going to scale fairly well across time. It doesn't have the downsides that Paxos does because the conflict resolution happens elsewhere in the database. This is just another example using map. So in the system I mentioned I designed a couple years ago for time series data for server metrics, we had this concept of labels that you could apply to messages, which would be things like what version of Linux is the server running, what version of Ruby is the application running. And these aren't metrics per se, but we want them bundled with the messages because they change over time. They might be redundant for a while, but when they change, that's really important. When you're tracking down a problem with performance and you find a change in a version of software, that might be the key to finding what the problem was. Almost always is. Inexplicable performance loss. Look at the versions of the language runtime and you find that somebody upgraded or downgraded a component, and then go look at the release notes and find this got faster or this got slower. More times than I care to count. So those labels are just key value. Instead of, in the old data model that we had in the application at the time, it was just serialized JSON. But if I was building it again today, I would be using maps directly in the table to represent those. And these I can, over time, as updates come in, of course it was a time series schema, they really shouldn't be updated. But we could have a process in this version where a separate batch process could come along and add additional attributes to messages. And it would all be safe. And it would be consistent for readers and writers. So finally, lightweight transactions. I saw this earlier. It's based on Paxos. It's very expensive compared to the normal write path in Cassandra. And so all of the talking about read, modify, write that I've done previously really brings me to this point. When you do the, even in Cassandra, which is very famously fast at writing, when you enter the world of Paxos, performance gets much, much worse. So it's more about making it possible to do these things than it is for them being fast. And we're going to make them as fast as we can, no doubt about it. The discussion comes up regularly at DataStax and in the community about how we can make these even better. Because for the application developers, which is hopefully you, it's making it easier. It's going to make your life better. It's going to save you time. And that's why we put them in. So what they do is they let you provide a constraint when you modify data so that you can be guaranteed that all the other clients in your distributed system, so all of your application tiers when a write goes into the database and a client reads it at the same time, in the same second or the same microsecond, you can be guaranteed that the database won't give either one of those operations a bad error, or at least give it an unexpected value is the most important thing. So by saying if username equal Renus, that was my handle when I played Final Fantasy XI. When I signed up, all the handles I liked were gone. And so I was sitting there trying to think of a name. And I just thought, well, maybe I'll try a Unix command. And I went through a bunch of Unix commands and finally came across renice, which is for prioritizing processes on Unix. And it turned out to be wonderfully nerdy. And it sounds nice. So that's what I played as. And so if I want to update my username down the road, so my original choice was Tobert, that's what I've been known as since I was a teenager. if I wanted to switch back, I need to verify if I click the button 15 times really fast, or maybe if I'm being an evil user and I have two computers running and I try to do it both at the same time. I need to make sure that I don't update twice with the wrong value. So maybe one update comes in as TOBER and the other one comes in as TOBERT. And that's what this does for you. So it guarantees that if it gets switched to TOBER, the update that tries to set it to Tobert is going to fail because the first one succeeded, and your client's going to get a message that Jonathan showed earlier, letting you know that your transaction didn't go through. So we've eliminated the question. Now your application can make a decision on what to do. You can return a 500 to the client if it's a web application, throw an exception, whatever is appropriate for your application. Then the other one is the if not exists. So this is for purely inserting. Now, it might be tempting to use this when you're doing something like a time series or one of these insert only workloads like content addressable storage. But I don't recommend doing that because that would affect your write throughput. This is for when you're doing things like, and I use the users as my example on purpose, when you have something like a user table that has a very low rate of updates. And when you do update it, it has to be correct. You know, you're doing ledger accounting, for example. The amount of change that you're making in the database is very low compared to maybe the amount of reads. You know, an auction house in a game, right? If you have users able to sell items, and when somebody clicks buy on an item, you have to guarantee that only that user gets the item to avoid things like duplication errors or to avoid just unhappy customers. And so that's when you should use these. So, in conclusion, all of our businesses, regardless of what kind of business it is, in the world of big data and exploding internet usage, are being inundated with data. And the reality is this is kind of the pitch for big data, but if you're not tracking your users, errors from your users, and when they're using your application, and on what platforms, and these are all things that you would use these models that I presented for. If you're not tracking those things, you're at a disadvantage because your competitors are doing it. That's what we all did as a business. Many of our customers are using this data to feed back into their business and find ways to make their customers happier, to sell more products, to make better products. Doing A/B testing, figuring out if putting the yes button on the left or the right, or switching them around, is going to make users make more accurate choices and be happier and be return customers. So your data models and your applications need to change to keep up. The data model that you use with MySQL or Oracle or MS SQL isn't going to work the same way. And one of the tempting downsides, and I call it a downside, and it's also an upside, again, trade-offs to CQL, is it's so familiar. And it would be tempting to say, this looks familiar. I can take my MySQL schema and copy it to Cassandra, change a few things, and load it through CQL, and I can use my old data model. But the reality is you're not going to get the throughput that you expect because you don't have an application architecture and a data model matched up to allow that high throughput write, high throughput reads that these newer systems like Cassandra are able to provide. Once you move to these architectures, you can start to gather that data, tracking really high resolution metrics inside your applications, tracking function calls I've seen, where people are finding hot paths in their code by recording function calls into out of a distributed system into Cassandra, and looking at that data to figure out how to optimize. But you can be doing it with customer data as well. You could be, it could be customers passing through a store and figuring out when they pass by certain items, if they see them at a certain height, do they buy it more often or not? That's big data. That's a lot of data. And it's a really hard and heavy stream of data. So, getting away from read, modify, write. This is a problem in the Linux kernel. When SCO sued some American companies a few years ago over copyrighted code that they claimed in the Linux kernel. One of the main things they were suing over was the copy on write algorithm. And what that was all about is avoiding the read, modify, write for when a process was forked. In old style Unix code before threads, and even still today, when you want to do parallelism, you use fork. And if you have to, at that point in time when the user calls fork, you have to copy the entire context of the process in memory before you can make modifications to that context. That's very expensive. And so when they said, we'll just say we made a copy, and then when a page gets modified, when the new client makes a modification to the memory to a particular address, it'll just make a copy at that point. So this was a huge performance benefit. It's just another example of when you're thinking about these data models, read, modify, write is one of those guiding principles. Am I doing a read, modify, write, and do I need it? Can I get away from it? And if I can, my performance potential is going to be much higher. And finally, Cassandra is, as far as the technological landscape goes, one of the top, probably the premier database. I can say it's the premier database for these kinds of applications, specifically because we made the choices to make the database available for high write throughput by avoiding these kinds of synchronizations that are required for read, modify, write. And that's how the whole thing works all the way through the database. From the messaging architecture to the way that compaction works, you saw Jonathan present earlier, all of these tricks were put in place to make it possible to scale horizontally. And if you start to back that up in your app, or start to use those same principles in your application, the same kind of write throughput will be available to your application as well. And for when you don't, we give you the tools for when you can't avoid it, we give you the tools to do it. Arigato gozaimasu.